Hello, so I want to make a video about using the oscilloscopes in phone repair and laptop repairs. I know it's not a tool that everybody has, and I know it's a tool, the oscilloscope is a tool that many people are reluctant to use it. Also, I need to mention that it's not a must to have one. You can repair phones and laptops just fine without the oscilloscope. You can base, for example, you can use only your multimeter, you can use a microscope and your soldering iron, and you're good to go. But there's cases where it really comes in handy, and I'm not an expert in using one because I started using them not very long ago, so I'm still adjusting. But there's actually situations where it helps me a lot. I will not go into extremely more details about how it helps me, but I want to make a presentation about how they work, the different types of oscilloscopes. For example, here you can see an old analog oscilloscope, and up here you can see a newer digital oscilloscope. Well, it's not actually, it is new, it's bought a few months ago, but actually this model is being made since 2016, I believe, if I'm not mistaken. I still believe it's the best value for the best money for value. It's very good, so it's cheap and it has a lot of features. You can find a lot of presentations online. So this is a 50 megahertz oscilloscope with 4 channels. You don't necessarily need 4. For phone repair I need at least 2, yeah, and it has 1 gigs of samples per second, the storage part of the oscilloscopes. This one here, it's 100 megahertz, and it has also 4 channels. So you'll say, okay, 100 megahertz is far better than the digital one that's only 50. And yes, from the megahertz perspective, but other than that, an old school analog oscilloscope doesn't help you very much, almost at all, in phone repairs, because in phone repairs I use the digital one to inspect the I2C communication. The difference between the digital and the analog is that the analog can display a result only if it's repeating. So you get a signal that repeats and that you can investigate. So for example, the I2C communication is a repeating process, but it's not repeating like a sine wave, or it's kind of repeats, it stops, then repeats again, and you can maybe see it. We can look at it a bit later, but I can show you, for example, using laptops. This is a laptop here, right? So we see here a buck converter. We can actually, I think this is the 5-volt supply. So if I go, let's do like this, right? Can you see the multimeter there? Not really. Let me take it here. So now if I measure here, I'm gonna put one probe to ground and the other one on this coil. You can see this is the 3.3 volt line, right? 3.3, and the other one is the 5-volt line, right? and this is driven by these two MOSFETs, which have in the background a driver, right? So let's see what happens if we power on the analog oscilloscope. It takes some time to load. Okay, to power on. Let me try to switch the camera. Still don't think you're seeing pretty well, but I'm gonna touch, for example, this coil. Let me enlarge the trace intensity so you can see it better, and let's go like this, right? So now I'm on that coil. That's a signal that keeps repeating, and it's driving actually the coil. We can see it here on the screen because it triggers it. I actually have a trigger on this probe, so I can keep triggering it. 1 second, the camera just froze. Let me start it again. Alright, so you can see I trigger, I'm triggering it, I'm triggering it, and so on. Yeah, ignore the volts peak to peak and the DC voltage there. So this is the 3.3 line. Let's see if we can modify the cursors. Okay, so the horizontal ones are automatic, we cannot modify it. But for example, let's say we are interested to see the frequency. This is switching, so I can just modify the time base. Alright, so we have now several occurrences here, and let's grab the cursors. Right, so we need the horizontal ones, and you see I'm going from from here to here. We have about 70 kilohertz, right? So it tells us that the frequency is actually 70 kilohertz. Let's go to the multimeter. Okay, let's set this to hertz. Alright, and let me connect there and see if the scope is correct. And you see it's actually 70 kilohertz. So that's actually an interesting thing that we can find out using the oscilloscope. Alright, so as we saw, if we're going like this, yeah, we can see actually the amplitude of the signal, which is showing it to us. Now I think we can achieve something similar with the digital oscilloscope. Let's power that on and see how it is looking over there. Let me reduce this one so we don't burn the screen. Alright, and let's power on. the one above. This will take some time to power on. Alright, so I'm gonna turn off channel 2. I'm gonna do kind of a similar setting. We're gonna set the vertical to 5 volts. We're gonna set it to AC coupling. Alright, and let's see what we are getting here with the digital oscilloscope. We modified the horizontal. Let me put it somehow like that so you can see actually what's going on. Oh, sorry, wrong knob. So we are here on 5 microseconds. It's kind of similar to what we were up there. I can grab a single shot. So this is the difference between an analog, you saw the analog how it looked, and this is the digital oscilloscope. This is so fine that we cannot actually measure the frequency here and have the courses, although it shows us here that it's 70 kilohertz, so it's already measuring it. But for example, the nice thing is, let me also show you the, so you see I'm now connected with the probe there. You can see the probe on the coil, and now for example on the digital one I can grab a single shot. Right, I have a trigger here set up, so it triggers on this line, on the, I think it triggers on the falling edge, so it triggers actually on this line that is falling here. If, right, you see, we got our single shot. Look now on the picture, I'm gonna remove the probe. So basically, if this was an analog scope, let me connect also the analog. Right, so analog is connected now. Look here, I have the signal there, but once I get the probe out, signal goes away. Again, I'm displaying the signal. There is absolutely no option on an analog scope to grab a shot of this signal. So there's nothing for me to do but just remove the probe and the signal is gone. Now, with the analog, with the digital, you see, my probe is not there. I can make it run again. Now it runs just like the analog one. You can see the signal here on the screen. And if I want a snapshot of that, I just get a single shot, right? And we already see that the signal is at 70 kilohertz. It has a volts peak to peak of 25 and an RMS voltage of 4 volts. I think the results were kind of similar on the analog scope also. Yeah, so now for example, let me switch the camera. For example, here I can increase the signal. I can have a look at it. You can have different measurements. You can also get cursors here, and you can play along with this signal. So this is actually great. it's something that an analog scope will never be able to do. Good, so let me pause this for a second and get back to phones and see how it works over using them for phone repairs, right? I'm gonna pause, I'm gonna prepare a phone board on the desk and get back to you. Alright, so we have here a iPhone 12 Pro board is this one, right? So the easiest thing to check if a coil is working actually on it is just grab the probe and hover it over that coil. Let me switch you to the screen. Alright, so you can see the oscilloscope screen, and here you can see we can actually just grab the pulses over those coils, so we know that the coils are engaged and working. This one, for example, is not. Yeah, here we can see a signal. Again, we can see the signal. Yeah, so this is something that an analog scope would really help you in phone repairs, but this is extremely rarely we use something like that. Let me switch the settings back. It's like 20 microseconds. Alright, so we actually use this for I2C communication. So for example, can I share this screen? No, I can't show you the screen. So I2C is a communication protocol that was invented by Philips actually, and on that protocol we have various chips communicating. Now if, for example, we already know that ZXW, for example, has let me switch you. I'm trying to switch the other screen. It's a bit difficult for me to explain everything, so you need to be a little patient. We know that ZXW has, for example, the schematics for iPhone 12, and let me show you. We have here on the screen, I can open ZXW, and we can open the iPhone 12 Pro Max schematic. Right, let me see if I can open the schematic like this, part name, to search in schema. Home series 12 Pro Max. Okay, we get the core. Alright, so here on the core, let me show you something interesting. So these I2C lines, for example, the simplest and fastest one we can find is on the battery. So the battery has an I2C2 SMC SDA. That means that it's the data line and it has a clock line. Both are 1V8. So for example, now let me show you here. Let me switch back to the dual camera. Yeah, I'm gonna connect the digital oscilloscope. See, we have two channels, right? Actually you can't see. This is the digital one, and I have two channels connected here. One is clock, the other one is data. So on this something is interfering here with the probe. Right, I'm gonna leave it aside like that. On the battery socket, I've connected two wires like this one. One is the clock, one is the data. I'm not sure exactly which is which, so I'm just gonna connect them random here to the oscilloscope. Alright, I'm gonna connect in the other line too. Alright, so you see that both lines are being pulled up. That's because this is a pull-up line, so it's being pulled up, and when they communicate, they pull it down. Do you notice something there on the screen? Let me prepare the trigger. Let's try to trigger here a single shot. See if it occurs. Doesn't. Oh man, I think I hit auto. Jesus. Okay, let me take it back. 1 volt. And the other one is 1 volt. What I don't like is that the vertical controls for both the channels are here. So there's actually one knob that you can control both of them. Right, so we have here the channels. Let me bring down channel 2 a bit. Okay, bring up channel 1. So we already see that something is actually happening there. Yeah, let me move the trigger. Let's move the trigger here and do a single shot. Okay, so we can see here a communication. This looks like a clock line, so I got them right. They are connected correctly. Now, this is something we cannot do on the analog scope, because again, we cannot freeze whatever is happening on the screen. Another important thing here, for example, this oscilloscope can also decode the I2C protocol. So you see, I already have an address there. Now let me put it like this, a bit small. Alright, I'm gonna move the trigger to the left so we can grab a lot of communication, and I'm gonna do another single shot. So now you see, we cannot read exactly what the addresses are, but for example, we can go to the event table and display the event table, and we see that it goes to address E2 16 16. Let me give you a close-up, right? So it's going to E2 to 16 and to 16. Now on the iPhone 12 we already know which chips are communicating on these addresses. Let me open the document and we're gonna have a look together on it. Alright, so to understand what is actually communicating here, I explained you that we have in the iPhone 12 schematics all the lines that are included in the I2C communication. So for example, here I have a file where I have all the I2C lines, and the ones that we were looking at are it was this SMC I2C2 line, right? The clock and data, and we can see here, I'm not sure if you can see good, let me enlarge it. We can see that there is a communication between Yance and Veridian. So we have the E2 address and 16 address that we can actually see them here communicating. I grabbed another shot. We can see here E2, E2 16, another single shot, E2 16. So we know that both are actually up and communicating. Thus, if we have a problem, for example, this is a very good investigation if we have problems on the charging circuit, because this communication actually takes place on the charging circuit. If there is a problem with it, usually we do not see those lines being up. Like, let me show you here. Damn, I clicked auto again. I shouldn't have to. Let me turn off the decoder. Alright, let's set back the channels as they were. I had, I think, 1 volt on the vertical. Channel 1. I've lost my channel 1. Oh, there it is. As I said, this is a bit annoying. Yeah, so we see these lines are up. Now look what happens when I'm gonna turn off the power on the phone. We're gonna see that those lines will come back down to 0. See? So now the phone is off. Let's have a look on the analog scope and see how these channels look like in analog. And of course we have no way to freeze it and get a snapshot. We can just see them like rolling. Maybe, I'm not very sure, but I'm connecting the probes now, and we can have a look and see how is it looking. So I have both probes connected. Let me switch on to the analog scope. Trace intensity. Okay, so we have channel 1. I'm gonna bring it a bit up. We have 1 volt per division. We have channel 2 here. Alright, and let me try to power on the phone somehow. You see the channels are currently at 0. And in theory, if I see something here, yeah, you saw that the lines went up, both of them. Okay, and the phone is booting, and we can already see. Can you see the communication? So we can briefly see there what is going on. It will not trigger because the signal doesn't repeat, so it's just a random signal here. Let me see if we can get it more obvious like that. But it's not. Here, if I bring the trace to maximum intensity, unfortunately, 1 second, because the camera froze. Alright, so signal is now at maximum intensity. And we can see bits and pieces of information. I'm not sure if we can see on the camera, see here, like when it's communicating, but there is absolutely no way for us to stop it, and of course there's no option to decode these signals, but we can at least see that they are communicating. So this analog scope helps us in multiple ways. We can see that actually the lines go up. If there is a problem with Yan, say for example, the lines usually are not being pulled up anymore, so we know there is a problem on the charging side. Yeah, but that's kind of the end of the analog scope compared to the digital that you've previously seen. Yeah, so that's kind of a difference in using an analog versus a digital oscilloscope, and there's actually, you can still find like CRT oscilloscopes that are kind of a digital, so they have a digital board and they are able to store some data. You can freeze this screen, for example, but they do not decode stuff, so that's everything they do. They can just freeze upon a trigger and display that information. But this is the main difference. These analog scopes are good for audio applications or signals that are repeating. I like they are a bit cleaner than the digital one, but both are very nice devices. So I don't know if you can afford it, and if you think it's useful, I strongly suggest to get at least the digital one, because that really helps you. But you need a digital oscilloscope for phone repairs that knows how to trigger the I2C protocol and how to decode it. Otherwise, it's just like an analog one. Maybe it's nicer because you can trigger and do single shots on different situations. Alright, so I think this is it. I didn't want to go very in-depth with this video. I just wanted to show you other means to diagnose a phone or a laptop, and you can extrapolate. If you're interested in oscilloscopes, you can definitely find like tons of videos online, and you can easily learn how to use them. Alright, see you later, bye.